Hello and welcome back. So last class we were discussing about the consequences of having a thinner electrolyte, wherein we saw that if the thickness of the electrolyte decreases, we can see that the resistance, although it gets decreased linearly, however there are consequences of losing the mechanical strength of the electrolyte, and will also eventually lead to electrical shorting. And that is why we have to make sure that the resistance is also minimum, and the thickness or the strength of the electrolyte also is not disturbed much. So let's see and discuss how these resistances that we have discussed so far, particularly in ohmic zone, look like. So let me quickly draw this fuel cell schematic one more time. So if we let's have, this is an electrolyte. So let's say this is the resistance of the electrolyte. So this is our electrolyte and this is our ionic, right. So now we are going to draw the electrical circuit of the fuel cell. Let me draw electrodes with different color. So this is anode and cathode. So please remember, these are the material resistances. So this is our anode and our cathode. Then we have something called as bipolar plate. So let's draw it with different color. Right. So this, I am going to draw the material resistance of this bipolar plate. So this is our bipolar plate anode, bipolar plate cathode. We are going to introduce one more resistance in the circuit. So I am giving some space in between. So this is the resistance of bipolar plate of anode, and this is resistance of bipolar plate cathode. And let's introduce one more resistance, which is at the interface of electrode and the bipolar plate, wherever they touch each other. So that is where the resistance gets added, and this is at the face between two faces. So it is called as interfacial contact resistance. So this is R, ICR on the anode side. So let me say it anode, and this is R, ICR on cathode side. So this is called as interfacial contact resistance. And since it is between two faces, as we can see, these two faces are basically the face of the bipolar plate, where it touches the anode or the diffusion layer. So that is the interface, that is where the contact resistance gets generated on the anode side. Same is the case with the interface between the cathode and the bipolar plate on the cathode side. So this is very important, as we can see that the rest of the resistances are arising from the material perspective, whereas this is the resistance that arises due to the contact between the two different components. So as we can see, all these resistances are in series combination. So all the resistances get added in series combination. And as we can see the magnitude of these resistances, we can see the R ionic is fairly large. The anode and cathode resistances as well as the bipolar plate resistances are quite smaller compared to the contact resistances and the ionic resistances. So, out of this all these resistances, the contact resistance and the ionic resistance, they dominate the entire resistance of the cell. So, let me write this R ionic is basically the resistance of the electrolyte, which we have seen this before, and Ra is the resistance of anode. This is the material resistance, which in turn talks about the resistance, that is the electrical resistance of the diffusion layer and so on and so forth. Similarly, we have Rc, which is resistance of cathode. This is again from the material perspective. Then we have resistance of bipolar plate from the anode side. So, this is the resistance of the anodic bipolar plate. So, again from the materials perspective. So, when I say materials perspective, we are not including the contact resistance in this resistance, and then we have resistance of the cathodic bipolar plate. It is again the material resistance, and this is the interfacial contact resistance on anode side. So, typically it is between, let me write this in bracket. So, between the anode GDL and the bipolar plate on the anode side. Okay. And what is the case in case with respect to the contact resistance on the cathodic side? So, it is R ICR on cathode side. It is the interfacial contact resistance on cathodic side. So, it is typically the between cathode GDL and bipolar plate on the cathode side. So, typically this R ohmic resistance that we talk, it is sum of all these resistances, So, let us write this down. So, let us start with R BPP anode. We also have few more auxiliary components such as current collectors. However, it is not included in this portion of the discussion. Then we have R ICRA plus R anode plus R ionic plus R cathode plus R RCR cathode plus R bipolar plate cathode. Let us take this R ionic on one side and ICR. So, this is total ICR. So, this is basically R ICR anode plus R ICR cathode plus R electrical. So, this electrical resistance, this typically include the material resistances. So, R anode plus R cathode plus R bipolar plate anode plus R bipolar plate cathode, right. So, if I generalize this, let me write this again. So, R ohmic is sum of R ionic plus R ICR plus R electrical resistance. Now, since if we compare this electrical resistance with the rest of the two, that is ionic resistance and the contact resistance, we see that normally electrical resistance, that is the resistance offered by individual cell components, is fairly low compared to the contact resistance and the ionic resistance. So, we can neglect this electrical resistance, and by and large it becomes that the ohmic resistance is sum of ionic resistance and the contact resistance. So, let me write this up. Since the electrical conductivities of individual cell components, that is when you say anode, cathode. So, when I say anode cathode, I primarily mean anodic GDL and cathodic GDL. Then we have the bipolar plates, anode and bipolar plate cathode, etc. We can also include the current collectors if needed. So, all these are, so electrical conductivities of the cell components are very high, since that implies that the R electrical is negligible compared to ionic and ICR. Therefore, we can write as ohmic is almost equal to ionic and RICR. So, let us quickly understand what this interfacial contact resistance means. So, let us say significance of interfacial contact resistance. Why are we so very concerned about it? So, what happens is, let me only take the one side, that is, let us say hydrogen side, and so we have this So, if you look at the contact, we have contact here and then here, right. So, this is the interfacial contact. So, let me write this is the interfacial contact. In other words, this is the contact between two faces of the components. So, when the protons are generated, protons and electrons are generated at the catalyst layer here. So, this is our catalyst layer. So, protons, they travel towards the electrolyte, bulk of the electrolyte, whereas electrons, they jump back from the triple phase boundary to the diffusion layer. So, this is all our diffusion layer. So, this is gas diffusion layer actually. Which we call it as GDL, and from once they reach the gas diffusion layer, they now try to jump across this interface and get into the bipolar plate. and once they reach the bipolar plate, they can be taken out from in the external circuit, and then we can take them to the cathodic side. Or we can also have a current collector at the end of the bipolar plate, which can again facilitate for this electron transfer in the external circuit. Now, main issue is when the electrons are generated at this triple phase boundary, since the catalyst layer is highly electrically conducting, so is the gas diffusion layer. There is not much difference that electrons feel when they change the material, when they travel from catalyst layer to the diffusion layer. So, since there is not much change that they observe, the resistance offered for those electrons to travel from catalyst layer to the diffusion layer is not much. However, this is not the case when they try to cross this interfacial contact between the bipolar plate and the diffusion layer. Since the bipolar plate and the diffusion layer are made from different materials and the contact is also not very perfect, there is resistance offered to these electrons while they try to cross this facial contact, and that is why this resistance, in turn we call this as resistance as interfacial contact resistance, because there is a lot of resistance offered to the electrons while they get transferred to the bipolar plate. So, this is why the interfacial contact resistance comes into picture, and this resistance escalates, or this resistance basically becomes more important as the size of the cell increases, and we will look at what different factors decide the value or the magnitude of this contact resistance. We will look that in the upcoming this session. So, let me write this RICR depends on many factors. So, first is the surface roughness of the gas diffusion layer and bipolar plate, or the monopolar plate in case of single cell. So, let me take the first case when the surface roughness is very high. So, what is happening is, if you look at this GDL and bipolar plate interaction, so if I try to zoom in here, what I can see is, this is, let us say, the diffusion layer, and the bipolar plate is also very rough. So, this is just sample representation. So, if we look at this the contact, so this is the bipolar plate and this is our GDL. Let us say both are rough or one of them is rough. So, we can see that the contact is not at every point. The contact between these two materials or components is very limited. You may expect these are the local contact. So, since we have not many points where these two materials are connected, so you can see the actual contact. We can say that these are the actual contacts between GDL and bipolar plate is very low. And where does this lead to? Since we have the electron generated at the catalyst layer, and since they travel from catalyst layer to the gas diffusion layer, now once they reach the diffusion layer, they have only limited contact points to travel from diffusion layer to the bipolar plate. So, in other words, the pathways for the electron transfer from GDL to the bipolar plate is very limited. So, let me write that up. So, pathways for this implies for this for electrons to travel from GDL to bipolar plate is very limited, and as we understand, if the pathways for the electrons is very limited, this leads to resistance. Or in other words, resistance to electron flow across the interface. So, interface means the phase in between the, or that is shared between bipolar plate and the diffusion layer. So, that is where the resistance gets added. This is the case when the surface roughness is high, and this bipolar plate, when we say the roughness is high, let us say this is uncoated bipolar plate. So, this is uncoated bipolar plate. So, we will see what happens when the bipolar plate is coated or when diffusion layer is also coated. So, second case is low roughness, low surface roughness means the polished bipolar plate, polished and or coated bipolar plate. So, let me draw that figure one more time. Now, the bipolar plate is also coated, so it will have not many surface roughnesses. So, it is fairly smooth, and this is the GDL with MPL. So, this is GDL plus MPL. So, we have seen what MPL means. It is a microporous layer which gets added on the top of diffusion layer for smoother contact between the gas diffusion layer and the bipolar plate. And this one is the coated bipolar plate. So, let us say this coated bipolar plate. So, coated means we have to have anti-corrosive coating on these metal bipolar plates. These coatings can be from titanium nitrides or chromium nitrides. You can also go for platinum coating, and there are so many coatings available. So, once we have this bipolar plates coated, the roughness of this bipolar plate gets reduced drastically. So, we can say that the typical roughness is around 5 microns. So, what happens here? So, once we have very low roughness with respect to diffusion layer as well as the bipolar plate, we have better contact. Better contact between the GDL and bipolar plate. So, once we have a better contact between GDL and the bipolar plate, where does this lead to? So, we can see that. So, we have many number of contact points, or these are the places where both of these materials are touching each other. So, many contact points, and that is what leads to lower resistance for electrons to flow across the interface. And as we know, once we have the low resistance across this interface, in other words, the contact resistance will be lower. So, this is the reason why we have to have a coated bipolar plates and the diffusion layer with microporous layer, because that brings more pathways for the electrons to flow across this interface. Whether it is a fuel cell on the anode side, then the electrons will flow from GDL to bipolar plate, and on the cathode side the electrons will flow from bipolar plate to the diffusion layer and vice versa. So, this coatings on the bipolar plate as well as on MPL, they reduce the surface roughness, and that is where the contact resistance can be fairly minimum. Second case, as we can see, is the clamping, and how does this clamping affect the contact resistance of the cell. So, let me draw this diagram. So, see that all these components are basically clamped using nuts and bolts. So, we have, so these are the nuts and bolts, at every corner of the cell. So, entire assembly is basically clamped together to hold this all components very firmly between the nuts and bolts. So, let me write that up. So, whether it is a fuel cell or electrolyzer, are typically clamped together using nuts and bolts. So, when the area of this cell is small, or when the cell is small, say let us say 50 centimeter square or so, the contact between the diffusion layer and the bipolar plate on the anodic side as well as on the cathodic side is fairly good. However, if the area of the cell is increased, then because of these bolts which are typically used for clamping, they are at the very edge of the cell, and that is why that leads to the local bending of these materials, which eventually leads to uneven contact at the interface of this GDL and the bipolar plate. So, let me write this. So, for smaller cells means typically area is around less than 50 centimeter square or so. This is a very approximate number. All the cells, all the cell components are in good contact with each other. So, what does this mean? This implies the contact resistance for such cell is minimum. However, in case of large cells, or when the size of the cell increases, what happens? Cell components typically bipolar plate and the bipolar plate, which is metal bipolar plate, I would say, especially observe local bending, and this leads to poor contact between GDL and the bipolar plate. And as we have seen, if this poor contact between diffusion layer and bipolar plate is there, your the contact resistance is bound to increase. Therefore, to minimize contact resistance, what we should do? We should have good contact between GDL and bipolar plate. And how we can have a good contact between GDL and bipolar plate? We should have contact pressure at this interface should be good. So, good means typically 1 megapascal of contact pressure is supposed to be a good contact pressure. So, let me write that typically around 1 megapascal of contact pressure is considered to be good in terms of the pressure. So, we will discuss more about this contact pressure in the upcoming class. I will stop here. Thank you.